We will begin with a discussion of the running coupling in QCD. This is the standard textbook result, what you see in the particle data group and so forth. The coupling runs, it runs from being strong to weak, and it's weaker than Coulombic at large scales. The question we ask ourselves is what happens in the infrared? The scale of 1 GeV corresponds to just about 1/5 of a Fermi, 0.2 Fermi. So this is why I say that the interaction is known only over a small volume inside the proton, because perturbation theory only works up till about 0.2 Fermi. When people began to see this, as I said in the first lecture, they imagined that this might continue to grow up to infinity. And they thought that was good because a coupling that was infinite would probably be confining. But if a coupling were infinite, you might have trouble with all sorts of other things. In perturbation theory, there is a Landau pole. The running coupling diverges at lambda QCD. It's log of Q squared over lambda QCD squared. Lambda QCD is not zero. Lambda QCD is about 0.2 GeV. And if there were this Landau pole in the infrared, it would affect all observables. We would probably have seen it by now. If the running coupling diverges at some scale, then observables might also diverge at that scale, because nothing would be defined properly in terms of this coupling. So you wouldn't really want the Landau pole that you see in perturbation theory to have any impact on observable physics. It ought to somehow go away. The Landau pole in QED doesn't hurt you because it's so far in the ultraviolet that the theory is broken down by then anyway. It screens itself by being embedded in some larger theory. QCD, we are confronted with that because the Landau pole lives in the infrared. We are all infrared physics, so we have to deal with this. We have to find out what saves us from being affected by this Landau pole. Returning to QED, it has a running coupling. In fact, in quantum field theories defined in 4 space-time dimensions, all couplings and masses come to depend on a scale. And that scale can often be related to the energy or the momentum at which a process occurs. So if it's a high-energy process, the coupling is sampled at high energies, so it's the perturbative coupling. As you start to run down in energies, you start to feel the impact of this growth of the coupling. The archetype, the first time we saw this was in QED. Owing to the water identity, there are, as I said the other day, 3 independent, apparently, divergences in QED. This one is the quark, also the fermion gauge boson vertex. This one is the quark wave function normalization, just the quark propagator. And this one's actually a vacuum polarization diagram. And this one is the quark-gluon vertex. The renormalization of the propagator, the vertex, and the gluon propagator have 3 independent divergences. But the water density means that Z1 equals Z2. So there's only one divergence left in QED to worry about, the Z3, because Z1 and Z2 cancel each other. In this vacuum polarization then, you have all the information about the evolution of quantities with scale in QED. And that is why you can study the photon vacuum polarization in order to obtain the running coupling. Running couplings come from the study of the evolution of the renormalization constants. The evolution of the beta function comes from studying the evolution of the renormalization constants with the scale. If these 2 cancel, that's all you have left. And so you have a single running coupling in QED, very obviously determined by the running of the vacuum polarization. So the running of the coupling is determined completely in QED by the photon vacuum polarization. You compute all of these processes, getting this Dyson-Springer equation for the photon vacuum polarization, and that will give you the running of the coupling. In QED, it's known to great accuracy, and the running has been observed directly. You can see this. You take the coupling at our scale, and the coupling is different at the Z boson scale, and the way it's different is completely determined by perturbation theory. You can calculate it. At first sight, when you add QCD to the standard model, it doesn't qualitatively change anything. Although there are 4 possibly distinct strong interaction vertices in the renormalized theory. You have a gluon ghost vertex, a 3 gluon vertex, the 4 gluon vertex, and the gluon quark vertex. All of those need renormalization. They're not all independent. The gauge symmetry gets promoted in QED to QCD via so-called BRST symmetry. This is not quite the same as the simple gauge symmetry of QED because the ghost fields have to evolve. You add additional fields, they mix with the gauge boson field, and that sort of relationships give you ratios of renormalization constants that are the same. That ensures that there should be a single running coupling that characterizes all 4 interactions on the perturbative domain. But this is not a simple question. If you have to define your running coupling from a vertex, all sorts of different issues arise. 4 different vertices, they should all be the same, but vertices depend on momentum flows. If I have a vertex, let's look at the 3 gluon vertex, for example. I have momenta K1, K2, K3. I want a running coupling. The normal running coupling we think about depends on one argument. Which one of these shall I choose to be that argument? Should I choose some combination of them? What scale? So these questions open up. There is no unique definition of a running coupling in QCD via the vertex. We avoided that in QED because we went straight to the vacuum polarization because there was only one vertex renormalization constant, and that was eaten by the wave function renormalization. So it's very hard to decide on what is the unambiguous running coupling. Perturbatively, it's easy. You can just go to high scales, make these all the same, and things run. But what happens in the infrared? So we have 4 individual and apparently UV divergent interaction vertices. So there are possibly 4 distinct couplings and any number of rearrangements of these momenta. How many distinct running couplings exist in QCD then, non-perturbatively? And which vertex should you use and which arrangement of momenta? Well, the answer is that there is, in fact, a unique running coupling, but it can't easily be extracted using the standard techniques. The reason that should be true is that otherwise you have possibly very different renormalization group invariant mass scales for each coupling. If I had 4 scales, 4 couplings, why should I believe that every one of those couplings has the same infrared scale? I'd have to prove it. It would be a very messy job. BRST symmetry could be broken because the couplings could run differently in the infrared. And then QCD could end up being non-renormalizable in the infrared. So you have a theory which is renormalizable in the ultraviolet, but it breaks down in the infrared because there are the 4 couplings that you had diverge, they have different scales, they might not all be the same. Well, there's no empirical evidence to support any of these conclusions. QCD does seem to be well defined because we're here, and this probable infrared generation of masses could be what's saving us in this sector. And that's actually what will happen, as we'll see. So in QED, as we saw, it's the water density that makes it possible for us to get the running coupling and a unique running coupling by considering just one diagram. When you look at the vacuum polarization, there's just one momentum. It's the momentum of the line, and that solves that question. So ideally, you would like to get a running coupling in QCD from the gluon vacuum polarization. The problem with that is that there's no water density. So the vertex renormalization here, these propagator renormalizations, do not simply cancel in the standard approach to the analysis of the green functions in QCD. Partly because the ghost fields are playing a role in any covariant gauge. There is one approach to this problem, and that is to use a combination of the pinch technique, which capitalizes on the analytic properties of the diagrams involved, and the so-called background field method, which is to first of all introduce some colored background field through which the gluons are propagating, look at mixed diagrams with these terms in it, and finally to remove the background field. So it's a mathematical procedure developed over some 30, 40 years to rearrange the diagrams in the vacuum polarization so that they look more QED-like. You gather up the diagrams into gauge invariant subclasses, and that way you can organize your analysis in a very simple mathematical way that enables you to have QED-like water densities. When you do this, you can obtain a single running coupling via the gauge boson vacuum polarization, and because it is expressed through the vacuum polarization only, it's process independent. It's the same thing no matter which objects are considered to be scattering. Two gluons, a gluon and a quark, ghosts and gluons. That's important. He wanted to have a unique coupling, and it has to appear everywhere at the same time. So one analyzes the gauge boson vacuum polarization, one uses this background field method and pinch technique, and then you arrive at a very simple expression for this pinch technique background field method propagator and the interaction. This is the ghost gluon vertex function, and here we have a ghost gluon vacuum polarization. We're solving, computing loop diagrams in the gauge sector to determine this running coupling. The ghost function gets dressed, so we pick up an F from that. This is a special longitudinal piece of the gluon ghost scattering. And the quantity we obtain here, this D, is renormalization group invariant, and it's the same thing I showed you yesterday that brings together the analysis of the gauge sector with the phenomenology that started by trying to describe hadron physics. This quantity D is the object that actually appears in the gap equation for the quark, in the beta salpeter kernel, and so forth. That's the process-independent part of this interaction. So, you simply in words, which is all I'm going to do here, I'm not going to go through the mathematics, you can rearrange the diagrams in the gauge sector of QCD to make sure that you have water identity looking structures so that you can get a unique running coupling from the gluon vacuum polarization. That can be compared directly with results from lattice QCD and experiment, as we'll see. That's being computed, this quantity D, and that's the result. You can see that it saturates in the infrared. This is basically the running coupling. It has the perturbative results out there, as we'll emphasize again soon, but it saturates in the infrared. There is no Landau pole in QCD. The reason is that the gluon acquires a mass in the infrared. So the Landau pole that you have in perturbation theory is derived because the gluon is massless, and you introduce the renormalization group invariant scale. In effect, you can replace this by the renormalization group invariant gluon mass scale. And that's the screening effect. It stops the coupling from diverging in the infrared. The scale of this is then the infrared scale of the coupling divided by the mass squared of the gluon. This takes us back to the analysis of chiral symmetry breaking in the Nambu approach. I had a mass scale for the gluon there. If I took that gluon mass scale to be too large, remember, we lost dynamical chiral symmetry breaking. So it's telling us that phenomena are placing a constraint on this ratio, alpha on m naught squared. If the coupling was too small, or if the gluon mass is too large, there would be no chiral symmetry breaking dynamically. We wouldn't be here. But we have to have this saturation, there has to be some gluon mass, to screen us from the Landau pole in the infrared. Otherwise, the theory couldn't make sense. So gluon cannibalism is saving us from the Landau pole. Yeah. What was the question? What's the meaning of this Yes, okay. What we're showing here is its renormalization group invariant. It doesn't matter what I choose to be the renormalization scale, the coupling sits one on top of the other. So there's no dependence on the renormalization procedure. So you want that to be a feature of your running coupling. You can now derive a renormalization group invariant product and compare this to other analyses and extract what the running coupling is, this process-independent running coupling. You introduce a propagator, put the mass scale for the gluon in there, and you can get a propagator back that you can compare with other studies. This process-independent running coupling is the d hat I described divided by this d. On any domain in which perturbation theory is valid, this is just the normal running coupling. It's an algebraic result, as we'll come to see. But it is a unique extension or infrared completion of the running coupling of QCD that we needed to find, what we wanted to find. This is process independent, as I mentioned. The same function appears irrespective of the initial and final states. Therefore, it's going to unify a diverse array of hadron properties. It's in the dress quark self-energy, it's in the beta salpeter kernel, and therefore it describes all of the observables you want. And it doesn't care about the flavor of the system, so it's going through all of the systems. It's enough to know this in Landau gauge, because the form of this ratio is independent of the gauge you choose, and any response to a gauge transformation is just going to produce a phase which is absorbed into the phase of the propagator. So it doesn't have any observable impacts. I just wanted to highlight that in these covariant gauges, the ghost gluon dynamics is playing a role. Not in the far infrared, where the ghosts decouple, and not in the far ultraviolet, where it's purely perturbative, but in the intermediate region, there's a factor of 2 change, according to whether you understand gluon dynamics properly or not. So the ghosts are not physically observable degrees of freedom, but they're an essential part of the mathematical formulation of QCD in a covariant gauge. They have a numerical impact, and for an observable, they must be included if you want to get the correct result for that observable. And this is physical in the sense that there is no Landau pole, and moreover, it saturates, therefore, at about a value of pi. Now, the value of this running coupling in the infrared is determined by what happens to the running coupling at some large scale. So when you compute this running coupling, you fix the value of the running coupling at, say, the tau lepton mass. You do it at some other scale, but somewhere at the perturbative domain, where you have measurements and you constrain your analysis. From that, you have a prediction for what the running coupling will be in the far infrared. It's a continuous function. Therefore, it's a prediction that follows from the evolution of the function. The value of pi is not something you put in by hand. It just happens to be that. I don't say it's pi to arbitrarily many decimal places, but for all practical purposes, it looks like pi within a few percent. This is valid at all space-like momenta, and as I just said, there's no matching procedure. So you have a unique Q-squared dependence for this running coupling on the entire domain of momenta. To get all of this to work, you had to know how the ghost and gauge sector interplay was working, how the gluons and ghosts interacted. And the study that was done here fixed the one scale by just asking the question, what is the ghost propagator at some ultraviolet scale, and compared it with lattice QCD. Then you fed it in and made the prediction for the running coupling. There are other ways to develop an image of what a running coupling might be. This is a procedure developed quite some time ago by Grunberg, and he has a process-dependent definition. Any particular process in QCD or in hadron physics has an expansion in terms of the running coupling. You can decide just to stop it at any order and say, I'm going to define this running coupling to be whatever is required to describe the data. You could do it for, in this case, the Bjorkane sum rule. You could choose some other process. The running couplings obtained this way would all be the same on the perturbative domain, but they'd be essentially different in the infrared. They'd be process-dependent charges. In principle, if you understood how to compute everything in QCD non-perturbatively, you could relate one charge to another charge using simple mathematical relationships. Or maybe they wouldn't be simple, they'd be quite complicated, because the expression for one process-dependent charge in terms of the other would involve infinitely many terms. So it wouldn't be a straightforward procedure. But in principle, it's possible. That is the drawback. It's a process dependence. You can't really make any firm conclusions about QCD in general from looking at one process. That's why the process-independent charge is of more value in some sense. The benefit of the Bjorkane sum rule as a choice is that it is known over a large range of k-squared. Its ultraviolet and infrared values are fixed because of the sum rule character. Certain observables have certain properties, so you know what the infrared limit is going to be and the ultraviolet limit must be. And it's an isospin non-singlet. And that means that all sorts of processes that would couple this coupling into the vacuum don't contribute, because it's carrying isospin, and any vacuum structures do not have isospin. Good morning, Stan. Stan walked in just in time because he's one of the first people to explore these process-dependent charges. We organized this earlier today. So we have this process-independent charge. I mentioned that we used continuum and lattice methods to analyze the gauge sector, brought them together. As I said yesterday, no approach alone can do this. We have to benefit, bring them all together to get as much information as possible. And because this charge is defined through the gauge boson vacuum polarization, it is the analog in QCD of the Gell-Mann-Low effective charge. You can look this name up in any textbook on quantum field theory and you'll find out why it's got this name. They're the first people to have done it in QED. And this is the result. The first calculation we did was this dot-dashed blue line. That result, we didn't quite have the gauge or the ghost sector correct. We did some reanalysis, and that took us to the red line. The dotted line here is something that Stan has produced. His process is charged from the ADS QCD model, where he tunes the parameter here and then matches it to the perturbative result. The general feature here is, as I said, you have a coupling. It's process independent, and it saturates in the infrared at about the value of pi. There is a qualitative change around here, and that's where the gluon mass sits. This is the screening effect I promised you. Perturbatively, it's running. It would normally have exploded, but the gluon mass kicks in, and that means that long wavelength gluons are screened from the theory. So no divergence is associated with long wavelength gluons. So the coupling saturates. The comparison with the Bjorkane sum rule process-dependent charge is quite remarkable. This is not put in by hand at all. To understand it, the first thing to realize is that you can analyze both the process-dependent charge and the process-independent charge in the perturbative domain. And you can prove simply and algebraically that these two couplings are exactly the same at leading order, good, and at next to leading order there's just a 4% difference. So in any domain that perturbation theory is valid, these two couplings are the same. So that's going back to this feature of the Bjorkane sum rule that I mentioned. It's an isovector sum rule. The same sorts of things that don't contribute to the process-dependent charge are also not contributing here. The same sorts of diagrams are being eliminated. This curve is the parameter-independent prediction. That is coming out. And what I said before is now important. Remember I showed you how the ghost gluon interaction shifted this from here up to there. And this emphasizes the point I made before, that you must really understand gauge sector dynamics in detail to make this prediction. If I chose to say I'm going to truncate QCD, or my procedure for dealing with QCD, such that ghosts were eliminated, covariant gauges, I could not possibly have obtained such a level of agreement. Put them in, not by fitting anything, but just by having the dynamics correctly represented, you have this perfect agreement with the Bjorkane-Summerall process-dependent charge on all the domain where the two are known. That's what this is saying, the isospin singlet part. So we have a unification of two very different approaches to understanding the infrared behavior of QCD. The process-dependent part, which is essentially phenomenological, data-based and process-dependent, and the other is deliberately computational, embedded in QCD using everything we know about the gauge sector to make the prediction for this running coupling. And the correspondence appears to suggest that that Bjorkane-Summerall, for the reasons I've described, is actually a way of measuring the process-independent charge for QCD. This alpha hat is a new type of effective charge. It's a direct analog of the Gell-Mann-Low coupling in QED, extracted now and used in QCD, because it's completely determined by the gauge boson two-point function. Process independent appears in every one of the dynamical equations of motion, and therefore it's known to unify a vast array of observables. It possesses an infrared stable fixed point. There is no Landau pole. And this is a semi-mathematical proof. It would be purely a mathematical proof if I didn't have to rely on lattice QCD to help me. I had to use lattice input in one place, and that was to set the scale and to ensure that my ghost propagator was correct. Yeah.
So just on that, what actually goes into ensuring that the ghost propagator is, what are you trying to match it to some?
Yes, very simply. The ghost propagator is the simplest thing you can calculate in QCD. It has one dressing function. It doesn't talk to very much. The vertices are trivial in Landau gauge. It's just one of the Slavnov-Taylor identities. It's a great thing to look at. Lattice QCD, therefore, studies the same thing. They have a curve for the dressing function. Continuum approaches have a curve for the dressing function. The curves are the same. What's the scale? Once we agree on the scale, then everything else is fixed. And that's what goes into this. So, this is almost a proof that QCD is infrared finite, owing to the dynamical generation of a gluon mass scale. The other thing about a gluon mass scale is it solves the other problem that people often worry about in QCD, and that is the Gribov ambiguity. In the neighborhood of perturbation, the perturbative domain, all gauge fields are unique. I do a gauge transformation, but only one of them lies on the trajectory. All gauge fields are equivalent only up to a single gauge transformation. There's only one gauge field on any trajectory. Non-perturbatively, I can have imagined very complicated gauge orbits. And if I fix the gauge, I might get more than one term on that gauge orbit. This is what Gribov noted, that there's no way to be sure that non-perturbatively you've selected only one gauge configuration. And it's quite likely that the number of gauge configurations on an orbit is infinite, because this is not necessarily a compact space. Normal quantization of field theories have non-compact descriptions of the gauge field. So there's no reason to expect you have a countable infinity of copies. So you could be in real trouble. This is an infrared effect. You get to these non-perturbative gauge configurations when you have long wavelength gluon modes that really sample long range. But if the gluon has a mass, all long wavelength modes are damped. They're screened. They can't feel the Gribov horizon. This was what Gribov himself postulated as a possible solution at the very beginning. He modified the gluon propagator, giving it what was an effective mass to stop it from feeling these Gribov copies. Here you see it happening dynamically in QCD. Gribov made up a model. Here you see it happening. The gauge sector produces a mass. That mass is just the size it needs to be to stop the gauge fields from feeling any Gribov copy. This means also that, so that means QCD is fine in the infrared. It's self-defining in the infrared. It is asymptotically free. That means we have good control over the ultraviolet behavior. These are the only things that can go wrong with a quantum field theory. You can have problems with the ultraviolet, you can have problems with the infrared. QCD is solving both of them by itself. It's therefore unique amongst known four-dimensional quantum field theories. It's potentially defined and internally consistent at all momenta. And this is why I said at the very beginning that QCD is actually a theory. We don't have to do anything to it. It is making itself defined by itself. And if this is the case, then it's conceivably the best place to look for physics beyond the standard model. Not in QCD itself, but in using this type of theory, strongly coupled, non-abelian gauge theories, to look for physics beyond the standard model, to make models for beyond the standard model physics. Composite Higgs particles, for example, can be described using generalized versions of QCD. And because they are internally self-consistent, there's no questions that you have to worry about. Most extensions of the standard model have all sorts of problems with divergences. But this type of theory is potentially free of all such problems. In 2008, Nambu was awarded half the Nobel Prize for the discovery of what the Nobel Prize committees erroneously called spontaneously broken symmetry. They meant dynamical. It's a very simple model. We discussed this yesterday. That simple line and the recognition that this can lead to dynamical chiral symmetry breaking won Nambu the Nobel Prize. You can look at this analogously via the gap equation. In fact, as we saw yesterday, a Nambu gap equation is the way of analyzing the model he proposed. Two functions, the wave function normalization and the mass function. This is what the mass function looks like in QCD. We know this now. This was a long-term prediction of continuum studies. Over time, methods were developed in lattice QCD to also compute the dressed quark propagator. And the points you see on these curves are the results of lattice simulations for the quark mass function. The coincidence or the confluence between all of these curves now make everybody aware, and everyone agrees that the quark mass runs in this fashion and it saturates like the gluon in the infrared. This part we already knew. This is the ultraviolet behavior. What we didn't know for sure was the red curve. This red curve is for the chiral limit. In perturbation theory, you can't see this curve because it's power law suppressed out here. The mass function behaves as 1 over p squared with some logarithmic corrections. Impossible to obtain in any perturbative calculation, as we've seen many times. I've emphasized a number of times, if I take the current quark mass to 0, then I can't generate a mass in the theory. This is a dynamically generated mass for the quarks. It is achieved because that effective coupling becomes large in the infrared, but saturates. And the saturation scale is given by a gluon mass of 1/2 the proton mass. All these things have to happen to make this scale about 1/3 of the proton mass. This is dynamical. We didn't add anything to QCD. This is pure gluodynamics that's driving this effect. If I put the quark feedback into the gluon sector, I get a bit of screening. But it's really the gluon dynamics and their own enforced self-saturation that's making this happen. It's the most important mass-generating mechanism for visible matter in the universe. It's responsible for 98% of the proton's mass. This, just by simple counting, 3 times 1/3 is 1. This is roughly the proton mass. It's that simple. If I started out here, I get 3 times 0 is nothing. There's none of the proton mass there. So it's an infrared probe feeling the infrared behavior of the dressed quark mass function. And that's the simplest way to understand the origin of the proton's mass. I can do it in many other more complicated ways, and they might be useful if I'm going to be working at very high scales, but they're not useful typically for you and I. We're at a very low scale. And the Higgs mechanism is therefore almost irrelevant to the proton mass. Experiments at JLab, for example, are sensitive now with the 12 GeV upgrade to this domain. And what does that mean? Well, of course, you can't directly measure the quark mass function. It's a quark property. Quarks don't exist in isolation. But quarks are part of every bound state. Quarks carry electric charge. I can scatter from them. So as I hit them with an electron and the electrons bounce off, this mass function evolution is going to influence the response of that quark to the electromagnetic probe. So I will, in the traditional fashion of particle and nuclear physics, by observing the scattering process, I can infer properties of the object from which I scatter, which is the charge-carrying dressed quark at low scales, or the charge-carrying parton quark at large scales. So this mass function is not directly measurable, but it's indirectly inferable from the scattering processes. We have looked at this very often. It looks very simple. I showed you an analysis of this diagram using the Nambu model yesterday. The thing about this that is hidden is that this is actually a countable infinity of diagrams. It looks like one diagram, but it's actually infinitely many. It includes this one. This is an alpha to the 23rd effect. It's in there. In QED, there are 12,672 diagrams at order alpha to the 5th. At order alpha to the 23rd, you can't count the number of diagrams that are present here. And in fact, it's impossible to compute this in perturbation theory. We don't have the mathematical tools to compute this diagram. There are so many overlapping divergences, we just can't cope. And yet, by doing this in the very simple way you saw yesterday, solving it self-consistently as an integral equation, the answer is there. I would like to illustrate now, going back again to the simple approach of Nambu, a very important result that underlies all of the features of dynamical mass generation, peculiar properties of the pion and the proton. And I can do this very simply because Nambu's model is so useful. Suppose one has a vector-vector interaction, just like QCD. It has a vector vertex at one end, a vector vertex at the other. And I'm going to assume it's strong enough to produce a dress quark mass in the absence of a Higgs coupling. All right? These are the assumptions. The questions I want to... Yes. Yeah. So suppose these points are given. Vector-vector, it's strong enough to produce a dress quark mass with no Higgs coupling. How do Nambu-Goldstone modes emerge? Do I have to do any fine-tuning at all to make them happen? And how does their mass vary with the current quark mass? And what do their properties reveal about the origin of mass for the proton and everything else? The pion is a pseudoscalar meson. It's a quark and an antiquark in the pseudoscalar channel. In a quantum mechanical picture, it would be one quark with spin up and one antiquark with spin down, and they'd be in the S wave. That would be a quantum mechanical picture. In a Poincare covariant quantum field theory, I must have 4 different amplitudes to describe the pion. A pseudoscalar has 4 amplitudes. These are the Pauli matrices because I have an isospin vector for the pion. P is the total momentum, and K is the relative momentum between the valence quark degrees of freedom. Remember, the valence quark. When I talk about a pion, it's a valence quark and a valence antiquark. That doesn't mean that if I take a snapshot at some infrared scale that those 2 degrees of freedom are all I have. Because the dressed quark has eaten up so much. The picture you have, if I insist on using a parton model basis, is the pion is infinitely many quarks, antiquarks and gluons. It's not simple in quantum field theory. I want to arrange the problem in such a way that I can make that tractable. This is the beta-salpeter equation for the bound state, pion. This should not be a surprise. The Lippmann-Schwinger equation in quantum mechanics is the same type of thing. You can solve bound state problems in quantum mechanics using the Schrödinger equation. That's fine. But you can also go a different way, and you can invert the Schrödinger operator and make it a green function, as we discussed on the first day. And you look for the poles in that inverse operator, and those poles give you the bound state masses, and the residues at those poles give you the wave function for the bound state. So the Lippmann-Schwinger approach to a bound state problem is just the same as a beta-salpeter equation approach to the bound state problem. So here we have quark, antiquark, scattering somehow to form the bound state amplitude. using the Nambu model is equivalent to making a simple truncation of this gap and beta salpeter equation. I put a bare vertex here, and it means the beta salpeter kernel has a bare vertex here and a bare vertex there. In this Hartree-Fock or rainbow ladder truncation, the interaction looks like this. Some propagator of sorts and the two vector vertices. Because of the saturation of the coupling, if I'm interested only in infrared effects, I can look at just focus my attention on the infrared, where the coupling looks like a constant. This is the Nambu model, after all. So this is how you see how the Nambu model arises from QCD. It's a useful, effective theory for low-energy observables because the coupling saturates. It would be useless otherwise. So the saturation of the coupling is what makes it possible to use the Nambu model to infer features of QCD at low energy scales. And of course, the model must break down when the scale of the process becomes bigger than this gluon mass scale, which is about half a GeV. In this case, the scattering is just a point. I had the distributed coupling, quark and antiquark scattering, but now I've taken it to a point, so I have a contact interaction. Since a contact interaction does not transfer relative momentum between the constituents, the bound state amplitude must become simple. The 5 terms I had before drop down to just 2, an E and an F with the gamma 5. Both of these, E and F, in the Nambu-like model, the contact interaction, are independent of the relative momentum. So I have a simplified beta salpeter amplitude for the pion in the contact interaction approach. I can now put all of this into the beta salpeter equation. Here is my quark, this is my antiquark, this is my quark. Here's the bound state amplitude. Here's the exchange through the vector. So it's just that diagram I wrote before with the terms put in place. This integral is obviously quadratically divergent. Look at the propagators there, each 1 over t slash. So the integrand is 1 over t squared. The integral has a measure factor of t squared. They cancel, so I have a quadratic divergence. This is the problem with the Nambu model. It's not a renormalizable theory. So you regularize it. Then the regularization parameter becomes part of the definition of the model. Also, the regularization scheme becomes part of the definition of the model. The same is true of the gap equation. This is the propagator we saw before for the model. So we have to now put this together and complete the definition of the theory. With such a propagator, the mass is the only part that's dynamically determined. So I change my gap equation, this, which gives me one equation for m, to be some regularized form of this integral, as yet to be defined. And what one can do is introduce a representation of the rational function, and then put a cutoff in the infrared and the ultraviolet. You don't need the infrared cutoff. The ultraviolet one you certainly do need to make the integrals finite. This is just a different version of the C function I used yesterday. Yesterday was a hard cutoff. Today I'm using something a little different with this heat kernel regularization of the integral. Do these integrals and you get something which is just a difference of incomplete gamma functions. These are easy to deal with using Mathematica, so it's straightforward to program them. As I said, this one is important from the terms of making the integrals finite. This one is not, because chirosymmetry is dynamically broken, there's an infrared cutoff being generated dynamically. But it's very useful. And the reason is that with this infrared cutoff, 1 over s plus m squared is now replaced by this combination. And that combination is, when s plus m squared would normally be 0, a difference of 2 numbers. It's finite. And that means there's no pole. So the point of including the infrared cutoff is to express quark confinement. So you can take this contact interaction, and instead of using a hard cutoff in the ultraviolet, putting another cutoff in the infrared as well, you can make up a confining model. And that makes it useful for a lot more things. For example, Nambu model can be used for the pion all the time. What about the rho meson? No, it breaks because the rho meson mass is too large. But using this scheme, you can deal with the rho meson as well. So if you want a toy to start to illustrate many aspects of the physics, this is a good way to go because it puts a confinement mechanism in for you. It doesn't mean that that's the way QCD works, but it is a practical tool for exploring the consequences of the absence of quark production thresholds in diagrams. A natural choice for the infrared scale is lambda QCD, so that's what we use, 0.24 GeV. You see this expression? That appears. Often when you calculate a beta salpeter kernel for something, for example, you might get this expression squared. Well, that doesn't cause you any problems because that expression squared is just the derivative of that, and so you can get a regularization of this function by just differentiating these things here. So you have a whole set of, whole array of processes you can study without using anything new. Just take derivatives. The next thing is that you want to preserve the Ward-Takahashi identities. Anytime you put in a cutoff, you start to break them. If you studied QCD properly, and you just put hard cutoffs into your integrals, you'd mess up all sorts of identities. You don't want that to happen. So what do people do? They use dimensional regularization. That allows you to do some translations of variables and verify that Ward identities are satisfied. We are interested in studying axial vector and vector Ward identities, current conservation and chiral symmetry preservation. If I define a model which explicitly breaks these symmetries, then it's dumb, because I can't possibly study the effect I want by breaking it at the start. So I have to be more intelligent than this. This is the axial vector Ward-Takahashi identity when the current quark mass is 0. It just says I have an axial vector vertex, and it's related to a difference, or in this case a sum, of the quark propagators. These things appear at every level in quantum field theory. That's what makes quantum field theory different to quantum mechanics. These expressions of off-shell current conservation laws. Because this is valid not just for the quark being on-shell, because it's not on-shell. It's valid for all momenta. And the axial vector vertex satisfies a very similar beta salpeter equation to the pion. If I put this dressed quark propagator in here, I need to make sure that the whole pair, this equation and this equation, are consistent. So let's do it. I look at this equation, I put the quantities in there, I work out what the final expressions are, and I get two. I get the first one and the second one. And this pair of conditions are required to satisfy the Ward-Takahashi identity. Well, the first one is simple. This is just the gap equation. So that's going to work because my dressed quark propagator satisfies the gap equation. So I know the first one is fine. The second one is different. For those people who do not consistently treat the Nambu model, they don't see this equation because they forget about the pseudo-vector part of the pion, the F term. But when the F term is present, this term is also present. It's entirely new. It says this Ward-Green-Takahashi identity is satisfied if and only if the model is regularized so that there are no quadratic or logarithmic divergences. Look at this. Q squared over Q squared squared is going to give me a logarithmic divergence. M squared over Q squared squared, no, this one gives me quadratic, that gives me logarithmic. So this can't possibly be 0 in any simple way. It's infinite. Both terms are infinite. But that happens all the time in quantum field theory. So I just say, okay, I'm going to regularize this content to direction. Symmetries are always preserved. This condition is just the same as employing dimensional regularization for the model. So it translates into this statement. This combination of those incomplete gamma functions must be 0. So whenever you see it, you put it to 0. And that completes the definition of the model. It's a model. You have to define it consistent with the phenomena you're going to study. If you don't do this, you should stop before even starting. So this is how you complete the definition of the model to study this phenomenon. Doing this, you arrive at a beta-salpeter equation in explicit form for the pion. And these are the entries in the kernel. This is one of the exercises. That's why I'm going through it in some detail. The first line, as we've already seen, is the gap equation. Plainly, therefore, if there's an M non-zero solution for the gap equation, then the Nambu-Goldstone mode exists. If M is non-zero, then E is going to be non-zero, so there's a pion. Remember, I had no current quark mass. The quark mass was generated dynamically. That effect is enough to make sure I have a pion. Equally, if E exists and is not zero, then the gap equation has an M non-zero solution. So that says that the appearance of a massless pion forces there to be a mass function for the quark. This is the fundamental aspect of quantum chromodynamics that makes it possible for the pion to emerge as a Goldstone mode. It says that the two-body problem and the one-body problem have to be the same in the pseudoscalar sector. This is fundamental. Most people, when they speak about Goldstone's theorem, don't mention this. It's discussed in terms of point meson degrees of freedom. You have some symmetry, you put some potential in there that breaks the symmetry, and then you get a Nambu-Goldstone mode because you've broken the symmetry spontaneously. That says nothing about the internal structure of the Goldstone modes that you're dealing with. It's completely different in QCD. Goldstone's theorem actually tells you what the internal structure of the bound state is. It says that the strength of the coupling to the channel is given by the dress quark mass function. And this can be easily extended to QCD because we've seen the pion beta subplanitude, we've seen the dress quark propagator. The simple illustration I provided for you there in an algebraic model that you can all do on one page can also be done for QCD. And what you find there is a collection of exact Wood or Goldberger-Treitman relations in QCD. They're exact in the chiral limit without correction. We'll get that later. And the miracle occurs again. The two-body problem is solved almost completely once you've solved the one-body problem. The mass function for the quark completely determines the pseudoscalar part of the pion. Exactly. There's no correction to this formula. So that is the most fundamental expression of Goldstone's theorem and dynamical chiral breaking in the standard model. It is model independent. We saw it emerge in Nambu's model. It's actually in Nambu's Nobel Prize winning paper, not written in this way, but it's there. It's gauge independent. It's true in any scheme I choose to set the gauge. And it's scheme independent. That means renormalization scheme independent. This is a feature of QCD. If the pion exists, then this relationship must be true. It's going to guarantee that the pion is massless. The pion exists if and only if mass is dynamically generated. Shall we take a break now for 5 minutes? All right. I enjoyed the break. I hope you did. We'll begin again now. So that relationship, as I emphasized, is really quite special. It's not in textbooks, typically. Textbooks do it a different way, so the textbooks ought to be revised. This is a statement that the quark-level Goldberger-Treitman relationships, those four identities I wrote down, have very far-reaching consequences inside the standard model. This statement that the one-body problem and the two-body problem are equivalent is very important. I've got myself messed up. That's what my question is. Yes?
This previous statement about pion exists is if and only if mass is dynamically generated. So if we have just one plate of quark, do we have dynamical generation of mass?
if you have one flavor of quark, you have to have the question of how is this related to the Goldstone mode? So yes, I can have a mass generation. I can make up a Goldstone. Can I still have a Goldstone mode in a one flavor theory? That would give me a U1 chiral symmetry, and that would be affected by an anomaly in QCD. And this equation doesn't work when there's an anomaly present. So if I have a U1 theory, I get the U1 anomaly. This gets an extra term on that equation, which stops it from happening. Mass is dynamically general, but the anomaly, there's an algebraic proof that the anomaly piece cancels this precisely. So the Fe equals 0. There's no pion. It's like saying, why is the eta prime not a Goldstone mode? In fact, that's basically the question you asked. The statement is not, so in the theory where the non-abelian anomaly, so this was the isovector channel, so the pion exists, the pion is an isovector. So this statement is completely general. You asked a question, if I have a theory where I'm dealing with an object which is not an isovector, is that a Goldstone mode? My answer to you is no, it's not, because of the non-abelian anomaly. Okay? Yes? Yes, it is actually. Because of this identity, as if you do the exercise, you can do it in the algebraic model, you will find that because of this identity, the beta salpeter equation has a solution for the pion which is massless. Because of this. So the beta salpeter equation for the pion has a mass equals 0 solution if and only if this identity is true. If this identity is not true, then the pion is stupidly massive. So yes, the simple answer to your question is yes. So Goldstone's theorem is fundamentally an expression of equivalence between the one and two body problems. And what that says finally is that enigmatically, the properties of the massless pion are the cleanest way to look at dynamical mass generation in the standard model, because the massless pion's wave function is a measure of the mass function for the quark, which is the origin of dynamical chiral symmetry breaking. This is part of the answer to the question we just had about the pion mass. Putting these things together, you can derive a mass formula, which is exact in QCD for the pseudoscalar sector, the flavor non-singlet pseudoscalar sector. This is the formula, and what it says is that the mass squared for a pseudoscalar hadron is equal to the sum of the current quark masses of the constituents. This term on the left-hand side is the leptonic decay constant for this state. It says, I take the pseudoscalar meson, I put the legs back on, and I let them annihilate. It's this diagram. It is the pseudo-vector decay constant for the pion. It says, how does the pion decay to a lepton and the neutrino? This is the process you would calculate. That's a matrix element, and that matrix element is this expression. So this leptonic decay constant multiplied by the mass squared for the pseudoscalar meson must be equal to the sum of the current quark masses multiplied by the pseudoscalar projection of the beta salpeter wave function onto the origin. This is the pseudo-vector projection here. I have gamma 5, gamma mu. The only change I make on the right-hand side is just gamma 5 goes there. I haven't derived this, but you can use the contact interaction to derive it as well. I can derive it in QCD, and the derivation is in here. And this identity is valid for any current quark mass. So it's valid for light quarks, it's valid for strange quarks, it's valid for top quarks. It's completely general. For any flavor non-singlet meson, pseudoscalar meson, this equation must hold. Let's consider the light quark case. M is near 0. If chiral symmetry is dynamically broken, then this must be non-zero. Why? Because the leptonic decay constant is an order parameter for chiral symmetry breaking. I can verify that too. The right-hand side is the chiral condensate. It is also an order parameter of dynamical chiral symmetry breaking. Both of these quantities have non-zero values in the chiral limit, and they're both independent of the current quark mass. And it follows from that there is a corollary. M squared for a pseudoscalar meson must grow as the current quark mass to the power 1 multiplied by some factors which are dynamically generated. This is what people typically call the Gell-Mann-Oakes-Renner relation. So this general expression has, as the low quark mass limit, the Gell-Mann-Oakes-Renner relation as a corollary. And I've emphasized this all the way along, that for a pseudoscalar meson, it's m squared that must rise as the current quark mass. The first derivation was in 1968. I'm going to go through that derivation in a little while, but that's the point. That is impossible in quantum mechanics. And this part of the expression is the so-called vacuum quark condensate. And as I'm going to explain, it has nothing to do with the vacuum. So this is something that Stan and I worked on together, and that's why I saved it for today. This is the orthodox picture of the QCD vacuum. There are people who imagine that the bound states are internally very simple. We have three things moving around perturbatively, and outside, all sorts of crazy non-perturbative dynamics is taking place. Now, the picture that they would have you believe is that to understand the properties of the proton, you need to know what's happening at an acausally connected part of the universe, because you have to know the condensate over there, you can't even reach it. So they would like you to believe that the properties of the protons in your body are determined by what's happening at a part of the universe that you can't even reach. That's the consequence of this assumption. And they like to think this for many reasons, and we'll talk about them, but this is the Gell-Mann-Oakes-Renner relation as it was originally formulated. This is the paper from 1968. It relates the mass squared of the pseudoscalar meson to an expectation value. And that expectation value is the expectation value of the chiral symmetry breaking term in the Hamiltonian for the theory inside the pion state. Gell-Mann-Oakes-Renner expression involves the pion state. It doesn't make direct reference to the vacuum. In 1968, QCD's current quarks were not yet invented, so they didn't know what U0 is. Today, we do. They then used PCAC, which I'll explain shortly, to make a connection between this expectation value and that one. And so the in-pion nature became lost because they were approximating this expectation value by an in-vacuum matrix element. PCAC just says that you can replace the pion field by the divergence of the axial current. This was an old idea. Weinberg is partly responsible for this. Many people were doing it. They couldn't solve a theory for the strong interaction because they didn't have one. So they were dealing with just simple S-matrix theory. S-matrix theory has certain properties: analyticity, unitarity, and so forth. You then write down all the sorts of relationships you can between matrix elements that must be preserved if these symmetries are true. Then you start to say, how can I estimate what the values of these matrix elements are? Well, the pion is light. Let's suppose that I can approximate the pion field by the divergence of the axial vector field in the neighborhood of small momenta. This is called then soft pion theorems. I have a state alpha, a state beta, and a pion in that state. Because the pion is replaced by this, then that is just replaced by the generator of chiral charges. So the pion field becomes just this commutator. And that means that I can do the same thing for pi-pi. I can replace the two pions here by a double commutator. And that replaces the in-pion matrix element with an in-vacuum matrix element. Not as a rigorous statement, but as a computational approximation. In those terms, we find that this is related to the in vacuum expectation value of the chiral symmetry breaking term as a computational approximation, not as a fundamental statement about the universe, but just how can I compute this? If that, as we now know it to be, is mq bar q, then the mass squared of the pion, which is the Hamiltonian in the pion state, is equal to that, or proportional to that. That's the derivation of the Gullman-Rene relation, another way. That's really good theoretical physics. They didn't know much, but they were able to derive this expression based on general properties of the S matrix. No one was thinking about how to define this quantity. It came to be called this vacuum quark condensate. So long as you think it's just a mass dimension quantity as an approximation to another matrix element, it doesn't matter. There is no problem. The problem arises if you start to think this is real, that there is some condensate which is space-time independent and has the same value over the entire universe, even that part of the universe which isn't existing yet. There was a warning at the time. This is a paper by Kasher and Susskind, and they observed the spontaneous breakdown of chiral symmetry is generally studied as a vacuum phenomenon. Because of an instability of the chirally invariant vacuum, the real vacuum is aligned into a chirally asymmetric configuration. On the other hand, an approach to quantum field theory exists in which the properties of the vacuum are not relevant. This is the light front quantization of the theory. These authors argue that dynamical chiral symmetry breaking can be realized as a property of hadrons instead of via some non-trivial vacuum exterior to the hadron. All you need, what you really need, is an enormous number of constituents. And that's just what exists in QCD. The partons that exist perturbatively, when you go to infrared scales, dress themselves. You cannot talk about a bound state being of a quark and an antiquark. It's infinitely many quarks, infinitely many antiquarks, infinitely many gluons. You have a countable degree, a countable infinity of degrees of freedom. The state emerges as a coherent superposition of all of these objects. That's what you need to have this effect. Now that was all fine, and then we had another group of people. They had a similar goal in mind. I want to compute hadron observables. I have matrix elements. I want to develop a scheme to make approximations to those matrix elements. And that scheme was called QCD sum rules. And in that approach, they had the chiral condensate for the quark, and they introduced the condensate, the so-called gluon condensate, this G squared term in there. Now, in their calculations, they don't write down a gluon condensate per se as the object they want to calculate. They write down some matrix element for a physical observable, and they try to develop an approximation scheme for its computation. And in doing so, they say, my gluon will propagate, and it will disappear into the vacuum, and I'll replace that by some non-zero value, some non-perturbative thing I don't know about. Where is the gluon? It's inside the hadron, of course, but they pretend it disappears into some vacuum, and they give it a number. This is fine. This is a great computational scheme. It's very effective. If you don't have a computer, which back then they didn't, then you have to develop an algebraic scheme to make estimates for physical quantities. At this point, however, the cat was really out of the bag. Up until 1980, there were basically no references to the vacuum condensates. Since that time, with these papers talking about vacuum condensates, there are some 18,000 references to a vacuum condensate. With this perception that the QCD vacuum is the vacuum state of quantum chromodynamics. It is an example of a non-perturbative vacuum state characterized by many non-vanishing condensates, such as the gluon condensate or the quark condensate, and these condensates characterize the normal phase or the confined phase of quark matter. This is what Wikipedia believes. Is there a precedent to this? Well, you all know there is. In the late 1800s, we imagined that the universe was filled with some material. It was called the luminiferous ether. We knew about water. We knew about waves in water. We knew about light. We thought light was a wave. Since waves need media through which to propagate, there must be something in the universe through which light propagates. Well, okay, if it's there and we're moving through it, we can measure it. So Michelson and Morley tried to do that. They tried to measure the ether wind. It is perhaps the most famous failed experiment to date. That experiment caused a lot of people to think, and it's actually what gave us in 1905 Einstein's special theory of relativity. So how should you approach this problem in QCD? This is the object that people think they're talking about. Are the quark and gluon condensates theoretically well defined? And is there a physical meaning to this quantity? Or is it just some mass dimension parameter in a theoretical computational procedure? If it's the latter, there's not a problem. We all have parameters we fit to data. Why does it matter? Well, it matters because of the way people think. We have a universe that we know began and it is expanding, but we've seen now that its rate of expansion seems to be accelerating. There are two pieces of evidence for this accelerating universe. One is the observation of type 1a supernovae. We think we know how these things burn. If we do that, then we can use them as standard candles, and their properties here, compared to their properties farther away, can tell us things. Their luminosity is a measure of distance, so we can use them to tell us how rapidly things are escaping from us. Another one is the cosmic microwave background and the anisotropy. It seems that our universe is right at the critical density. It is flat within errors. But the matter, including dark matter, adds up to just 1/3 of this critical density. 2/3 of the critical density is missing. Dark energy could be that 2/3. It has the right properties. It has negative pressure, which means it forces an expansion. And that would what you need to add to 0.33 to bring yourself up to a flat universe from a compact universe. There are cosmologists who have attributed this. In order to have escaped detection, this missing energy must be smoothly distributed. Fine. In order not to interfere with the formation of structure that would inhibit the growth of planets and suns, the energy density in this component, the dark energy, must change more slowly than was happening in the past. You can put expansion in there by putting back the cosmological constant of Einstein. He had it in there because he wanted to balance the effect of gravity. He didn't want the universe to be expanding, so he put lambda in there. But when he found out the universe was expanding, he threw it away. If you interpret it in terms of the cosmological constant, then the density observed associated with this is 10 to the minus 12 GeV to the fourth. That's the scale for the dark energy in the universe. Prominent cosmologists have argued that the advent of quantum field theory makes consideration of the cosmological constant obligatory, not optional. You have to put it back. The only possible covariant form for the energy of the quantum vacuum is this one, and that is mathematically equivalent to a cosmological constant. It's a perfect fluid, it's precisely spatially uniform, so vacuum energy is almost the perfect candidate for dark energy. These are not my words, they're Michael Turner's words. Well, that means that the QCD vacuum, so-called, is going to make a contribution. If chiral symmetry breaking is expressed in a non-zero expectation value of the quark bilinear in the vacuum, then the energy difference between the symmetric and the broken phases is of the order of the constituent quark mass, which we've seen is 1/3 of a GeV. If I put that into the expression, I get an answer which is 10 to the 46 times observation. This is one of the biggest embarrassments in theoretical physics. The prediction based on this notion is 46 orders of magnitude too large. If I put the Higgs boson in there, treated the same way, then I get 100 times too much, 100 orders of magnitude too much. There's something wrong with this concept of vacuum expectation values. Yeah, that's right, put them all together. If we go back to the picture that I was discussing previously, that the Higgs boson might be a composite, then this also goes away, because the expectation values are then locked up inside the states that form the Higgs. So how do you resolve this problem? I just pointed to it there. Are the condensates real, or is it just some parameter? Well, you can ask the question the way Weinberg would. What is measurable? I stated this before. Quantum field theory has no content beyond analyticity, unitarity, cluster decomposition, and symmetry. Cluster decomposition talks about confinement. You have to be able to separate clusters. We know that in hadron physics, in QCD, the only clusters you can celebrate are color singlet clusters. What's between them is nothing now. Everything that happens between separated clusters is exponentially down. There's no power law behavior there. That's what cluster decomposition means. It's a mathematical statement. And this brings us to some things that Stan and I and our friends have written about confinement and the condensates. Dynamical chiral breaking and its connection with the generalization of hadron masses has historically been viewed as a vacuum phenomenon. We argue that confinement makes such a position untenable. If quark-hadron duality is a reality in QCD, then condensates, those quantities that have commonly been viewed as constant empirical mass scales that fill all of space-time, are instead wholly contained within hadrons. That means they're properties of the hadrons themselves and expressed, for example, in their beta salpeter or light front wave functions. This is just what Kasher and Susskind said. You have this structure inside a hadron of infinitely many degrees of freedom. And the dynamics of these infinitely many degrees of freedom are what produce these non-trivial effects. And here is the simplest definition or expression of this. This is the Gell-Lennox-Renner relation, as written in the Gell-Lennox-Renner paper. It's equation 4.3. The mass squared of the pseudoscalar meson is the expectation value of the symmetry breaking term in the pion state. This is in the pion state. The unapproximated form of this relationship makes no reference to a vacuum quark condensate. So it's the same, but it's just interpreted differently. You can expand these ideas, and what you really find is that the mass squared of the pion is the current quark mass sum multiplied by this quantity. And this is just the scalar form factor of the pion at zero momentum transfer. It's a form factor, the scalar form factor. All form factors are the same. I strike an object with an electron, I get the electromagnetic form factor. I have a scalar probe, which is like the graviton, and I'm going to get the mass form factor. At zero, it's just the mass. So the mass of the pion is completely determined by the scalar form factor at the origin. That's just the pion scalar charge. So this is how you see it. I take a hadron. I have an operator. If that operator were gamma mu, then I would say I am measuring the charge of the hadron. If it's gamma mu gamma 5, I say I measure the actual charge of the hadron. If it's sigma, I measure the tensor charge of the hadron. If it's the identity, I get the scalar charge of the hadron. The scalar charge of the hadron is no more a property of the vacuum than its electric charge, its tensor charge, or its axial charge. It's a property of the state. So really, the picture is completely the opposite. The structure of QCD is completely tied up inside the hadrons, as it ought to be. There is a horribly complicated structure inside a hadron. But between the hadrons, it's basically perturbative. I have small fluctuations inside between these hadrons. The dynamics of QCD is taking place inside the hadron. There are many ways of seeing this. One more simple way is to say that I have a quark. I have an antiquark. These things are dress propagators. The chiral condensate, so-called, is one moment of the quark propagator. If the quarks are confined inside the hadron, then the condensate's confined inside the hadron too. The same is true for the gluon, and so forth. So, if you choose to change your paradigm and accept that the dynamics of QCD lives where QCD lives, and that is within hadrons, then you can solve this problem. It goes away because empty space is empty. What's happening is that all of these effects are tied up inside the hadron, and that means you've included their effect when you included the hadron mass in evaluating the energy density of the universe. You don't have to add something else as well. So it's already contained. There's no extra term to add, which is 10 to the 46 times what we observe. So putting the condensates back into the hadrons reduces the mismatch between experiment and theory by a factor of 10 to the 46, possibly by far more if technicolor-like theories are the correct paradigm for extending the standard model. What this says is that the divergence problem is solved. It's not 100 times or 150 times bigger than what we observe. It doesn't answer the question, what is the value? I can't tell you what the value is that produces this universe acceleration of expansion. I don't know. All I can say is that I can tell you for sure it's not anything to do with vacuum energy, because these things are properties of the objects you've already counted. So now we can come to some of the more important parts.
Can I just add one funny thing?
Yeah.
When I first found this Kasher-Susskind paper, I wrote a note immediately to Lenny Susskind. And I said, Lenny, that's a fantastic paper. You showed there's no vacuum condensate. It's a stank scan, but I forgot my own work.
Yeah. So let's suppose the quantum field theories are the correct paradigm for understanding nature. Our universe has 4 dimensions. Unless you believe in extra dimensions and supersymmetry and so forth, we deal with 4 dimensions. It's a critical point. Theories with D not 4 possess an extra dimension, an explicit dimension. So if I have more than 4 dimensions, I have uncontrollable ultraviolet divergences. I have a measure factor, it's D5, it's D6. I have measures of Q to the 4th, Q to the 6th, and so forth. My propagators have the same sort of 1 over Q slash structure, so I get all sorts of ridiculous ultraviolet divergences. So I can't formulate theories in beyond 4 dimensions. If I have less than 4 dimensions, then my couplings become mass dimensioned. If I have 3 dimensions, E squared has dimension 1. And that means the theory is super-renormalizable. It's ultraviolet finite. All quantities have power law behavior in the ultraviolet. D equals 4 is a critical point. You have theories which have logarithmic divergences, slow divergences you have to take control of. The standard model is built from scale-invariant classical field theories because such theories are renormalizable. That renormalization procedure introduces a mass scale, but the size of that mass scale is not determined by the theory. In the context of QCD, lambda QCD is what we arrive at, but we don't know what lambda QCD is. Experiment has to tell us. So the questions we like to ask ourselves is what determines this natural mass scale for visible matter? Why are we 1 GeV mass scales? And suppose we are 1 GeV mass scales. The other part of this question is, what if the mass scale was 1.1 GeV or 2 GeV? Could we still be here? How sensitive is our universe to the scale in which we find ourselves working? Can we answer that question within the standard model? You can perhaps, because you can make variations of the scale of the proton mass. If you can connect that with the pion mass, then you can start to ask the question, how does nuclear physics change? Is carbon still stable? Is the deuteron still stable? And these will tell you about the universe's evolution. So you can begin to answer this question. You can't answer what the scale is, but you can answer the question, what happens if I change that scale? If you can connect that scale to other observables and the ratios between them. I said this at the beginning. Our universe, as we know it, depends on a few empirical facts. The proton is massive. The mass scale for the proton is very different to that of electromagnetism. The proton is absolutely stable, despite being a composite object. Every other composite object we know breaks up on short time scales. The proton has lived longer than the age of the universe. We have never seen it decay. And the pion is unnaturally light. It's not massless, but it has a lepton-like mass, despite being a strong interacting composite, built from the same things that make up the proton. The pion decays, it decays quickly. This is emergence. We have low-level rules producing high-level phenomena with enormous complexity. This brings us to a sort of argument that's been going on for a long time. It's a determinism or reductionism to holism or emergence. Descartes was the first one to come up with a reductionist perspective. He imagined a duck was a machine, and he drew us a picture of how that machine might work. On the other side, this emergence, this holism, goes back to Aristotle. Emergent properties, the concept that the object as a whole is not explicable as just the sum of its parts. This type of philosophy has gone on for a long time, and the debate has gone on for a long time. And we're back to it again now. Is it possible for us to understand the emergence of ourselves from the Standard Model simply by solving that equation of QCD, that one line? Are we just that one line? Is even your thinking the responsibility, the result primarily of that one line? Because your neurons, after all, are made up of the same things. This is the Lagrangian of QCD. There is one mass scale. It's the current quark mass. That's where the Higgs boson gets into this picture. Its scale is 1/250th of the scale of the proton. That is very far removed from what we need. This nuclear physics mass scale is an emergent feature of the Standard Model, and no amount of staring at this can reveal that scale. We've looked at it for some 35 years, and we don't yet know, really, how the proton mass is generated. We have conjectures, we have calculations, but we can't really give you the bright picture. And suppose we do the proton correctly, what about its excited states? This is different to quantum electrodynamics. I can write down the QED Lagrangian. In that Lagrangian, I see the coupling and I see the electron mass. And the spectrum of hydrogen is given in terms of the coupling and the electron mass. So every scale I need in QED is visible. The scales I need for QCD are invisible. They emerge some other way. So what is mass and where is it hiding? I can think of this as a classical theory, as I stated. It's still a non-abelian local gauge theory. I can take the current quark mass away. Now the theory is scale invariant. There is no dynamics in a scale invariant theory, only kinematics. If I have a scale invariant theory, and you tell me that these two objects form a bound state this big, then I can say the theory is scale invariant. That's equivalent to a bound state this big, or this big, or this big. So bound states can't exist. There's no definition, there's no sense. There is only kinematics in a scale invariant theory. So classical QCD cannot describe us. Our universe can't exist. The Higgs boson doesn't solve the problem because the mass scale is too small. The bound states would be too big. So where did it all begin becomes the same as where did it all come from. What sets the mass scale? What scale is it? Lorentz invariance is not enough. You must add the effects of translations to get the whole Poincare invariance of the quantum field theory. In those circumstances, Poincare invariance entails that the energy momentum tensor must be conserved. There's a Noether current associated with scale transformations that has a dilation current, and if this is true, then you find the dilation current's divergence must be zero, because I have a scale invariant theory, and that means the trace of the energy momentum tensor must also vanish. So in a scale invariant theory, the energy momentum tensor must be traceless. Just 2 lines of algebra to prove this. Classically, therefore, in a scale invariant theory, the energy momentum tensor is traceless. But classical theories must be quantized in 4 dimensions. I regularize and I renormalize the ultraviolet divergences. And that gives us dimensional transmutation. We know, textbooks can tell you this, once I do this, all the quantities that were once constant come to depend on the scale at which I observe them. They become renormalization point dependent. There are certain quantities that aren't. Certain things are renormalization gauge or scheme independent, but most quantities depend on the scale. What does that mean? Well, the coupling becomes scale dependent. Then, under a scale transformation, I know that the coupling evolves because it's a scale transformation. I know how it evolves because this evolution just defines the theory's beta function. I can then insert these relationships into the Lagrangian and compute the divergence of the dilation current. It's just the divergence of the Lagrangian with respect to the scale. That's the beta function. And finally, I can relate the divergence of the dilation current with the beta function times g squared. That is the so-called trace anomaly. In a four-dimensional theory that has been renormalized and regularized and renormalized, there is a trace anomaly. The quantization of a renormalizable four-dimensional theory forces a non-zero value of this trace. So that's what happens. When you have a four-dimensional theory, you get a scale. You don't know what the scale is, but a scale must exist because you put it in by hand. It's not peculiar to QCD. It happens in QED as well. But it's a very small effect there. The electron mass is far greater than any effect of the trace anomaly in QED because gluons don't self-interact. Photons don't self-interact in any strong way. The form is the same, but the scale is completely different. Can we understand all of this? Yes, you can now, but we didn't before. The other connection, which I've emphasized many times, is that, again, classical chromodynamics, it's a non-abelian gauge theory. It has local gauge invariance. As I said the first day, I take three quarks. I put one here, I put one on the moon, one on the other side of the universe. I can do a color rotation of one of these quarks, and the others will respond, so the whole thing is a color singlet. But there's no notion of confinement there, because the scales are ridiculously large. Confinement is not a statement of color gauge invariance. It's a statement of color gauge invariance over a certain length scale. That's confinement. So three quarks and all of this must be close together. And you can't do that in a scale invariant theory. You need a mass scale. So the origin of confinement is connected with the origin of a mass scale. They can't be separate. So whence a mass is equivalent to whence a mass scale, and that's equivalent to whence a confinement scale. So understanding the origin of mass in QCD is quite likely inseparable from understanding confinement. And that is probably the same as understanding dynamical chirosymmetry breaking. So that's why I believe, and I can't prove it, but I imagine that they all are connected. Where is this mass? Well, knowing the trace anomaly exists doesn't tell you too much at all. It just says that there is a mass scale. I said this. QED has one. It doesn't tell you how big it is. Can you compute it or understand the magnitude? Well, no, I can't compute it, but I can measure it. I can put this energy momentum tensor in the proton state. Because of Poincare invariance, I know what the right-hand side must be. It's just P mu, where that's the proton's form momentum. I can take the trace. Taking the trace of this gives me P squared. That's just the proton mass squared. And that tells me that the expectation value of the trace anomaly in QCD inside the proton state must be the proton mass squared. It means that this trace anomaly is very large. It has a scale of 1 GeV squared. So in the chiral limit, the entirety of the proton's mass is produced by the trace anomaly. What is the trace anomaly? It's just G squared, the gluon field strength tensor squared, multiplied by the beta function. That means, from one way of looking at it, that all of the proton's mass is generated by glue. That's a valid description. I can't, and no one can at the moment, demonstrate that in a calculation. And the reason I can't is because if I do it this way, then the operator here is a parton model operator. It's defined with my operators being at a very high scale. In those terms, the proton wave function is ridiculously complicated. I have to make up a massive state. It must be a coherent state of all these partons and gluons, and I can't solve that problem. So I can't answer the question directly as a calculation. I might want to reformulate it. So I can answer the question. And there's another scale issue at hand. I can look at the same thing in the pion. When I do that, I get the answer of 0. I'm in the chiral limit. I have the same operator. I put it in a different state. In one case, it's 1 GeV squared. In the other, it's 0. Does that mean the scale anomaly somehow vanishes in the pion state? That gluons contribute nothing to the pion mass? Well, there are people who think that's true. They are lattice QCD practitioners. There are ways of looking at this question which lead you to conclude that the gluons don't contribute to the pion mass. But that's also not really correct, because that's a difficult way to obtain 0. It's easier to imagine that 0 owes to cancellations between different operator contributions. This operator is very simple on a parton model basis. It's just g squared times the beta function. But that's at very large scales. Operators evolve with scale. Operators mix as I evolve scale. So this simple operator at high energy scales can change to some different combination at low scales. And in terms of the operators defined at a low energy scale, the picture can be completely different. And that goes back to what I said at the beginning. Interpretations, pictures of physics, can depend in quantum field theory on the scale at which you look at them. The best answer, or the simplest way of obtaining the answer, might mean changing the perspective. And such precise cancellations cannot be an accident. It has to be 0. So no statement of the question, how does the mass of the proton arise, can be complete unless I also ask and solve the question, how does the pion remain massless? The natural scale of visible matter must emerge simultaneously with the apparent preservation of scale invariance in a related system. So the pion appears to be a scale invariant system because the trace anomaly in the pion is 0. In the proton, their value is 1. Our goal is to elucidate the entire array of consequences of the mechanism responsible for these two things. The electron-ion collider is supposed to understand or expose the origin of mass. It has to equally expose the origin of the absence of mass in a related state. Yeah.
You mentioned that in QED there is also a trace anomaly, but the effect is small. So, are there analogous relations in QED?
The answer to the one question is the trace anomaly is small in QED because the photons remain massless. You can make algebraic connections between the propagator or the inverse propagator for a gauge boson with the trace anomaly. You can see that in a hand-waving way by seeing the trace anomaly is related to g squared, and g squared is the inverse of the propagator. So there's a connection between the propagator's behavior and the appearance of a trace anomaly. Since QED propagators are simple, there's no trace anomaly. It's very small, it's just perturbative. QCD has a very strongly modified gluon propagator. You get a big trace anomaly. It's related to the gluon mass. In QED also, there's no gauge boson. So there's no case in which the trace anomaly vanishes. There's no QED bound state in which the trace anomaly vanishes. Another side of that is that we put a big scale in by hand, the electron mass, which far exceeds anything that QED can do. There's a whole array of scales in QED that prevent you from seeing any effects from the trace anomaly. No, there's no QED bound state in which this can be true. Well, the actually answer to this question is algebraic, if you look at it the right way. The pion has a Poincare invariant mass and a Poincare covariant wave function. They're obtained by solving a beta-Salpeter equation, and I showed you how to do that in this contact interaction approach. That's a scattering problem. In the chiral limits, I have two massless fermions interacting via exchange of massless gluons. The initial system is massless, and it remains massless at every order in perturbation theory. We've demonstrated this. In perturbation theory, I take a quark, antiquark partons, I scatter them, I sum up lots of diagrams, bit by bit. It was massive to start with, it's always massive. Sorry, it's massless to start with, it's always massless. But the complete calculation, as we've emphasized, is not just a sum of finitely many terms, it's an infinite sum of infinitely many terms, and this must be coupled with the gap equations for the quarks. So I must solve this scattering problem. Then, if I do that, I have many words, but the answer is very simple. I can prove algebraically that in quantum field theory, in the pseudoscalar channel, the dynamically generated mass of two fermions is precisely cancelled by the attractive interactions between them if and only if this is true. It is saying that the mass of the two dressed objects inside the bound state is precisely cancelled by the binding energy between them, so long as this identity is true. Then the pion is massless, without fine-tuning. If I put mass in there, I get the Gell-Mann-Oakes-Renner relation. So that's how it works. What this is saying is that the operator that is simple at very high scales changes as I come to low scales. I get the interaction energy, the two-particle irreducible part of this, and there's a one-body part that dresses the quarks, and that brings in the dressed quark mass. This term is negative, this term is positive, and the two things cancel. This is the mathematical explanation of why the trace anomaly vanishes in the pion, because of this operator evolution. If I insist on working at a high energy scale, then the pion wave function contains all of that information. All of these correlations, the coherent state feature of the pion bound state says that the simple operator talks to every piece of that pion wave function such that the cancellations take place. If I choose to allow my operators to evolve to a low scale, the answer becomes different, becomes simpler. I have dressed my quarks now. They acquire a large mass, they have a binding energy, and the two things cancel one against the other, algebraically. So this works because the cancellation takes place between these elements. It arises naturally because of the chiral symmetry and the pattern by which it's broken. And so in the chiral limit, the pion is massless, irrespective of the magnitude of any other hadron's mass. And that's the peculiar thing. It doesn't matter what the mass scale for the proton is, so long as the Higgs doesn't couple, the pion is always massless. I could have a 1 TeV proton. I could have a Planck mass proton, but the pion will still be massless. That's the importance of this exact cancellation. That's what drives so much of the pion physics. So I think we can stop there now, and we'll talk again tomorrow. Thank you for your attention. Were there any questions before we take a break?
I was just going to say that in my lecture, I'll give an example of how AES exactly there's a cancellation between what you call the trace term and the spin terms.
Yes.
So it's not between the two terms you have, but it's a different two terms.
It's a realization of this.
Then you get the rho pi mass.
Yeah.
But all the other words you said are just are materialized on this UAES. So then it has all the features you described, no condensates outside the hadrons.
Yeah.
Poincare invariant.
Yep. That's an important one. Okay. Then take a break.